Okay, guys. So we give the formal definition of the non-deterministic finite automata. And here's an example. So we are seeing this finite non-deterministic one. It is non-deterministic. How we can understand that? First, there's epsilon symbol. Second, Q1 has two possibilities for the input 1. Q2 has the third one. Q2 has no possible output for 1. We don't know what to do with Q2 if we read a 1. And for Q3, the same, but the input is 0. There is no possible output for the 0, right? So these are the things that we can understand. This is not a deterministic, but a non-deterministic one. So here's the definition, the formal definition. Again, it's still a 5 tuple. There are 5 items in a sequence. And the Q is a set of states, the same. Q1, Q2, Q3, and Q4. There are 4 states in Q1. There are 4 states in set of states are Q, right? And our input alphabet is 0 and 1. Again, we don't need to put epsilon symbol into our alphabet. We know that it is there, but we don't have to put it there. Okay, guys? And the transition function is basically changed drastically comparing to the deterministic finite automata. And what we can see is all of the symbols are now a set, a subset of the Q, right? So the range of the transition function is from Q and epsilon. It takes one state, one input, right? It goes to a power set of Q, right? So Q1, if we read a 1, if we read a 0, we stay on Q1. Q1, we read a 1, either on Q1 or Q2, right? So you can see how we process it. Right? This is transition function. For the one who's not possible, we use this empty symbol. And Q1 is start state. It is the same. We use the same arrow, same notation for the Q1 for the showing the start state. And F, our accept states, set of accept states, contains only Q4, so we put it there. So this is the formal definition of non-deterministic finite automata. And this is the formal definition for non-deterministic finite automata. And it should be the same, right? The only difference is that the Y is here like this. The alphabet changes here. And everything should be the same. Let me see. Rm must have R plus 1 equal to. Everything is the same. Okay, guys? So there's actually a question. So, which one is more powerful? Is there any language that we cannot show, depict, or accept with a different deterministic the DFA, deterministic finite automata? But we can accept it with a non-deterministic one. So you can think it like that. When I say which one is more powerful, it's something like that. So this is all the languages that deterministic finite automata accepts. These are the regular languages, right? So this is DFA. NFA is the same, but NFA accepts all the strings and nothing else, or NFA somehow a bigger set. Or I don't think anyone can say, but this is also possibilities, right? NFA is smaller set. Which one is true? And the answer is none of them is true. Because the answer is that DFA and NFA are equivalent. Okay, guys. DFA and NFA are equivalent in terms of computational power. Okay, guys. Two machines are equivalent if they recognize the same language. And all NFAs can be convertible into a DFA. Okay, guys, which means that For an NFA, it doesn't matter what it is. For an NFA, we can convert it to DFA that does exactly the same thing, that accepts the same language. Okay, guys. Therefore, since all the NFAs are convertible to a DFA, or you can find an equivalent DFA of an NFA, these two sets is equivalent. They are the same. They are computationally equivalent. Okay, guys. Here's the example, I think. Where is the example? Yeah, here it is. Here's the example, guys. So it looks not good, but it's like more complex, but still is working, right? You just need to more state, but you're able to do that. So this is how we do it. So here we have three elements. So this is how we can convert NFA to DFA. Okay, guys. So this is an NFA. You can say this is non-deterministic because we have that. Immediately we can say that. For 2A, there are two possibilities for the A. So this is non-deterministic, but for sure. To convert it to a DFA, what we need to do is, first, we have to create a state for all possible states. Okay, guys. There are three items. Which means that 2 to the 3, 8 possibilities, 8 possible, or number of the subset of this tree set, the Q, is 8, right? 2 to the 3. So that's why we have to do this 8 state. For each possibilities, we need to build this thing, right? For each set in power set. So the first one is nothing. What if there is nothing? Like there's no possibilities. 1, 2, 3, 1, 2, 1, 3, 2, 3, and 1, 2, 3. So which means that, right? So which means that based on the input, there are possibilities, right? There are possibilities that your NFA can be on states. For one input, your NFA can be on 2 states or more than 1 state. For all possibilities, basically you put a state. For example, if your NFA can be on both 1 and 2 with one input, you put a state for it, right? So this is depicted there. 1, 2 means that the NFA can be on either state 1 or 2 for both of them. Here's the example, right? So we are on 1, or let's say we talk about 2. We are on 2, right? With an A. We can be on 2 or B or 3, right? If we are on 2, we take an A. We are either be on 2 or 3. We are not showing this like this. We are not showing it like this. This is the wrong way. But we are doing this thing like this. If we are on 2 and with the A, you can be either on 2 and 3, you go to 3. Okay, guys? Because here, empty set means that there's no possibilities. 1 means that this is the only possible way. This is the only possible set that you can be on. 2 means that this is the only possible set that you can be on, right? 1, 2, 1 and 2 is the possible. 1 and 2 are the possible states that you can be on. 1, 2, 3, all the states that you can be on. Okay, guys. So this is the idea. So the start state is 1 and 3, right? Because like when you start, you can be on 3 as well by using the empty string. Okay, guys. So since the first idea is that after building the states, the epsilon symbol is a problem for us. We need to get rid of it, right? To do that, first we start from the starting state. If start state has some kind of epsilon, we have to take it as a start state. Accept states now are 1. 1 and 3 are the accept states, right? So all the inputs that have 1 and 2 are accepted. 1, 3, 1, 2, 1, 2, 3. Why not this 2, 3? 2, 3 also must be the right thing. I forgot to add it there. 2, 3. No, 2, 3 is not there. I'm sorry. Accept states are guys 1, of course. 1 or 2, which means that you are on the 1, right? 1 or 3, which means that you're on 1 as well. And 1, 2, 3. But why not 2, 3? Maybe either on 3 or 2. Yeah, 1, 3 is not accept state. Yeah, that's fine. Because 2, after you are 2 and 3, you can't go back to 1, right? That's why 2, 3 is not accepted. Okay, guys? Let's keep going. Then we have to do this transition function. The rules must be put there. So we have 8 of them, right? Let's do it. From 1, let me remove this 2 if I can. Okay, I got it. So how we do it? You are on 1. Based on input A, what you can do? From A, right? First, you can take this empty symbol, then A, you can be on 1. Is that true? If you are seeing a 1, if you are seeing an A, if you are on 1, right? If you read A, you have only one chance. Take the epsilon and go back. Or you can just, it's not possible for you because 1 doesn't have A directly. Is that clear, guys? For 2, with A, what you can do? You can be either on 2 or 3, which means that you take 2, 3. From 3, sorry, we forget B, right? From 1, if you read a B, you go to 2. Yes, we are converting to the DFA. So this is not a DFA, right? You say? I think it's going to be deleted by itself. I think it's going to be deleted by itself.